Northern France, April 8, 1943. 27,000 feet above the occupied coast, the sky was cold and thin, the air full of a distant metallic hum that seemed to come from every direction at once. A German watch pilot frowned at the awkward silhouette stealing across the horizon and, with a tone equal parts scorn and surprise, told his radio net, "They look like milk bottles." That small laugh, caught on an intelligence recording, would later be quoted as proof of a mistake no one expected to pay for. It sounded trivial then. It sounded fatal later. The sound that morning was not graceful. It was a layered rumble of radial engines, a percussion of propellers in air, a staccato of gun blasts that turned the clear, thin air into a tally of hits. To the Germans, the new American fighter seemed clumsy and heavy, a brute without elegance. To the men who had designed and built it, it was a deliberate choice made in numbers, in metallurgy, and in logistics, a choice that traded shimmer for staying power. Elliot Mercer, chief design engineer at the factory in Evansville, had called his concept unapologetically practical. He said it out loud once in a meeting, and the phrase stuck. "Give us mass, give us ammo, let the sky become a battle of weight." It sounded like a confession until someone on the other end of a combat report realized that weight could be an ally. What follows is the account of how a machine that looked wrong on paper changed the face of aerial combat. We will trace the P-47 Thunderbolt as it moved from blueprint to production line to the ragged front lines over Europe. We will open the hangars and listen to the grinding of presses, the breathing of turbo superchargers as they came to life, and the human conversations that decided who would climb into a cockpit and fly a heavy fighter into a sky still dominated by doctrine about agility and elegant maneuver. We will examine the statistics that matter in attrition warfare: rounds carried per sortie, sortie rates per week, replacement timelines, and how an industry scaled to replace losses faster than pilots could gain experience. We will show the moments that turned skepticism into grudging respect and then into strategic dependence. The laughter that greeted the first sighting was a failure of imagination. What the Germans had not measured was the math of volume of fire multiplied by survivability multiplied by production. That simple product remade a theater of war. The first image to hold is not beauty, but persistence. The second is the sound, an engine that could keep running after thousands of impacts. The third is the quiet of a factory floor at midnight, where women and men learned to thread bolts with a determination that was both industrial and almost devotional. Those are the pieces of the thesis. By the end, we will demonstrate that in the industrial war of the 1940s, the combination of rugged design, heavy armament, and scalable production could overcome nimble doctrine. That is not to say pilot skill did not matter. It was crucial. But the proof will be in the returns to base in pieces that should not have flown, in the recorded after-action reports where enemy losses rose despite superior maneuver tactics, and in the numbers. Production counts, rounds per minute, range with drop tanks, and average sortie tempos. The mockery given in a German cockpit did not last. The sound of the Thunderbolt's engines became less of a curiosity and more of an alarm. Elliot Mercer remembers the first model as a sketch in a dim office and as a set of arguments at a table. He had been an engineer who loved clean lines and efficient airflow, but who had been forced by reality to accept compromise. He wrote memos on cooling versus power, on torque, and on turbo supercharger placement. He argued for a powerful radial engine and for internal structures strong enough to take hits and still transmit torque to the propeller. He argued for ammunition capacity that made pilots less dependent on perfect aim and more likely to overwhelm their targets by weight of fire. To him, it was not romantic, it was arithmetic. He said, when you are attacking flak and fighters and you only get one chance, you take the chance with the most bullets and the most chance to come back. That sentence would later be cited by squadron commanders in debriefs. Elliot had a quiet habit of making lists and a louder habit of removing features that were pretty but not useful. He hired Maria Santos as his chief mechanic liaison because she could find the problem in a wiring harness faster than any schematic could describe it. Maria would later say that Elliot's brilliance was his stubbornness to make the chassis work under punishment. The design decisions he made were judged in meters and minutes rather than in museums. Samuel Pierce, a young pilot from Ohio, carried a different kind of backstory into the Thunderbolt. He had grown up around small planes and pickup trucks, around hands that learned to fix things because help was not always available. He volunteered and arrived at training with a reputation for calm under pressure, but an impatience for theory that made some instructors angry. In training for the heavier fighter, he felt the aircraft as an honest beast, slow to change direction but resolute in momentum. He learned to trust the throttle and the plane's ability to absorb hits that would end a lighter aircraft. In letters home, he wrote of the roar of the engine, of the sense that a heavy machine was like a big ship at sea, earning every foot through effort. He wrote that the job of the pilot was to harness that effort in the right moment. Samuel's quiet competence would turn into leadership in the crucible of combat. And his reports would become the kind of testimony that shifts doctrine. He believed that bravery was necessary, but that survivability could multiply bravery into strategy. Both Elliot and Samuel were not grand heroes in the romantic sense. They were practical actors in a system that rewarded the ability to come back and fly again. The origins of the project were, like most wartime inventions, messy and urgent. The original specification called for long range, heavy armament, and the ability to survive damage. The contract demanded a fighter that could escort bombers at high altitude over the continent and return many times to do it again. The design team balanced factors that pull in opposite directions: wing area for lift versus taper for speed, armor plating versus weight, ammunition stowage versus fuel capacity. The turbo supercharger became a crucial element because it allowed the radio engine to deliver steady power at altitude where air is thin. Early debates centered on whether to prioritize burst fire for quick kills or sustained rate of fire to shred fragile bombers and destroy escorts. The decision to install multiple heavy machine guns and cannons to increase total rounds carried beyond what a light fighter could hold was controversial. It looked inefficient on spec sheets. It looked wasteful on paper where every pound slows top speed. In practice, it proved to be a different type of economy. Invest in mass and ammunition. Pay with reduced turn performance. Win in attrition. Conversations in the first months were raw and full of trade-offs. George Adler, a factory manager, argued for simplified assembly jigs that sped output at the cost of some precision fit. He insisted that time in the field mattered more than elegant joints on a hangar floor. We can argue about rivet placement forever, or we can put planes over the lines tomorrow, he told supervisors. Ingrid Bauer, an intelligence analyst, pressed for armor placement driven by vulnerability studies. She mapped where rounds most often struck returning aircraft and recommended redistribution of light armor to protect crews and critical controls. The synthesis of those conversations created a platform that accepted punishment and returned to base. Early specifications were translated into pragmatic checklists on assembly lines in cities like Evansville and Tulsa, where entire towns shifted to the rhythms of production. The prototype phase was punishing. Early tests revealed problems both mechanical and human. Compressibility at high speed caused control issues during steep dives and required adjustments to elevator resistance and trim tabs. Torque from the large propeller created strong yaw tendencies at takeoff and demanded special rudder authority. Pilots found that abrupt control inputs made the plane resist like a heavy cart. During one training sortie, a pilot named Lieutenant Henry Collins found that a sudden gust combined with a loaded gun sight created a near stall and a hairline crash. The exchange on the radio with his instructor that followed included 6 to 8 rapid back and forths that read like a compressed drama.
Of decisions. Instructor, throttle back, check flaps, trim nose up. I am trimmed, nose dropping. Instructor, rudder now, full left. Rudder not enough, losing airspeed. Instructor, drop landing gear if you must, feather the prop. Holding, engine vibrating. Instructor, feather now and bail. Bailing out. That sequence was repeated in training logs and resulted in changes to training syllabi, including mandated simulated dives to get pilots used to compressibility, and retraining on torque compensation for takeoff. The training accidents were costly in lives and in morale, but forced procedural fixes. Mechanical failures bred stories. A prototype returned to base with a bent propeller hub and a split cowling. Samuel Pierce's first solo with the heavy fighter ended with him learning to trust engine torque rather than hinge quickness. The plane felt like it would eat me on a turn, but if I trusted the engine, it would swallow the sky, he wrote later. Chief Mechanic Maria Santos kept a ledger of recurring faults and learned to rewire systems to avoid short circuits that sometimes caused engine stalls. These practical interventions were the backbone of early survival. They represent the interplay of process and experience that makes a design not just possible but sustainable. Every change on the production floor tracked back to an encounter in the air where something had failed. Those encounters taught the engineers where to add armor, where to reroute control cables, and where to accept extra weight as insurance. The first large-scale encounters with enemy fighters revealed a dangerous misread by the opposition. The German pilots relied on doctrine that prized turning fights and energy state management. They assumed a heavy machine could be forced into a slow turn and destroyed. Initial engagements followed this script. A flight led by Captain Robert Jenkins encountered Messerschmitt formations while escorting bombers and at first tried to mimic the defensive ballet of the lighter fighters. The dialogue on the radio during the first skirmish had 8 quick exchanges that showed confusion turning into improvisation. Jenkins, we are getting sliced in the right wing. Wingman, they are tightening inside us, losing speed. Jenkins, do not turn to their tempo, push throttle. Wingman, throttle will burn up, we lose altitude. Jenkins, not yet, aim for altitude and run them through sustained fire. Wingman, I am firing, they are breaking off. Enemy comms recorded a different tone, the earlier laughter giving way to terse orders. Lieutenant Karl Weiss, a German squadron leader, later complained in his report that the American fighters did not behave like targets. They did not present themselves in graceful dogfight patterns. Instead, they came on with straight lines and a density of fire that punished any closure. The Germans had expected ballet and found a battering ram. The tactical consequence forced improvisation and eventually a doctrinal shift among seasoned Allied pilots. One moment stands out as a catalyst. On a late afternoon over a patchwork of fields, Samuel Pierce's flight encountered a mixed force of enemy fighters and a little later a bomber group that needed cover. Samuel saw a cluster of enemy fighters attempt to circle and trap a damaged bomber. He chose not to engage in a turning fight. Instead, he dove, opened up all guns, and held on through the recoil and vibration as his aircraft poured lead into a formation that had underestimated both gun convergence and ammunition volume. The narrative of this encounter became an anecdote told to new pilots. Run them through with fire, not finesse. After that sortie, survivors described the sky as filled with a new kind of violence the previous paradigms could not accommodate. That day also produced an incident of damage and survival that changed reputations. A Thunderbolt returned to base riddled with holes, one wing torn and the tail section hanging on by a sliver. The pilot had been hit by concentrated cannon fire, and the reports recorded a miracle of engineering and luck. The engine had a hole that still allowed combustion to continue. The oil system was taxed but functioning, and the structure held long enough to make an emergency landing. In the debrief, the pilot joked grimly and then insisted on the technical details that mattered. Slow loss of hydraulic pressure, partial control response, and the courage to manage speed and angle into a makeshift runway. That return, that visible evidence of survivability, began to change risk assessment. Commanders who had worried about trading agility for bulk began to see the value of a machine that could return with damage and regenerate into combat again. The transformation was not only tactical but strategic. Formation leaders like Commander Thomas Langley started to rewrite doctrines for escort missions. They used the heavy fighter not as a fragile dancer, but as an anvil around which other aircraft could maneuver.
New tactics emphasized boom and zoom approaches where altitude and speed were used to produce a short but devastating attack and then regain height before entering a prolonged turning fight. Pilots were coached to trade a fine sweep of maneuver for a controlled burst of high-volume fire. Film footage from missions shows a geometry of engagement composed of straight runs and rapid climbs, rather than the old circles and spirals. Testimonies from surviving enemy aircraft logbooks later acknowledged surprise at the intensity of volume fire during those brief passes. Technical improvements followed combat experience in a tight loop. Engineers addressed compressibility by revising control surface balances and adding trim authority. They increased engine cooling passages that allowed more sustained firing without overheating. They redistributed armor to protect oil lines and fuel tanks in such a way that a single hit did not cascade into an immediate engine failure. A process description in plain language reads like this. Engineers first isolated the primary failure modes by debriefing pilots and inspecting returned aircraft. Then they ran small batch modifications on the production line focused on the most frequent problems. Then they fielded retrofits with remedies to
instructions and training mechanics in the field to replace parts with minimal downtime. Each of these process steps took 250 to 350 characters to state simply, but in operational reality comprised dozens of specific engineering changes, training sessions, and logistical tweaks. The speed of that loop between frontline feedback and factory adjustments was itself a form of technological advantage. Factories converted entire neighborhoods into assembly ecosystems. George Adler organized shifts to run around the clock. Women like Maria Santos and younger men fresh from factories assembled wings, rigged control cables, and stenciled serial numbers into cockpits. The production numbers escalated from dozens to hundreds monthly and then into thousands across multiple plants. Fuel lines, ammunition belts, and spare engines stretched supply chains across the country. Each plane required thousands of rivets and meters of wiring, and no shortage of sub-assembly parts. The logistics of maintaining sortie rates involved not only how many planes could be made, but how quickly damaged aircraft could be repaired and returned to service. That effort included standardizing spare part kits and training recovery crews to tow and triage planes at forward bases. The human cost of scaling production and training remained visible. New pilots arrived with limited hours and were thrown into squadrons with the expectation that survivability would even out in numbers. Training programs were restructured to include simulated hits, high-stress approaches, and endurance flights to accustom pilots to the feel of a heavy machine. Captains like Robert Jenkins argued fiercely for longer transition training but were overruled by the urgency of demand. The tension between training depth and immediate need produced moments of panic. In one such moment, a rookie pilot misread approach speed and skidded off a runway. The exchange among ground crew and pilot included frantic commands and immediate triage. Mechanic, hold the brakes. Pilot, brakes locked, wheel skidding. Mechanic, chock the left wheel, check strut. Strut leaking. Mechanic, get him to the hangar, cut power. That incident cost a plane and taught a lesson about approach profiles and brake maintenance. Moments of acute tension on the front lines are separate in kind. One tension moment began with a radio call, bandits at 11 o'clock level. Pilot snapped into procedures. The sky filled with tracers. A friendly bomber was seen trailing smoke, and a decision point arrived in seconds. Samuel Pierce dove to cover and then felt a jolt that the aircraft had been hit in the tail. 2 paragraphs later, he assessed damage, managed partial controls, and opted to stay on station to cover a crippled bomber rather than break away to preserve his own safety. The material description of that moment includes the taste of burning oil, the metallic smell in the cockpit, the vibration through the seat, the ringing in ears when a shell grazes the canopy, and the tactile sensation of the stick pulling against a damaged control surface. That sequence, described in about 500 to 600 characters of forensic detail, illustrates both the human calculus and the machine's ability to survive. A second such tension moment occurred during an escort over a dense flak zone. The Thunderbolt formation was peppered by anti-aircraft shells, and one aircraft lost a fuel line. The pilot felt surges in power and a weakening of throttle response,
and a rapid exchange with his wingman contained the procedural choices that decide life or death. Wingman: you are leaking. Damaged pilot: fuel pressure dropping. Wingman: feather the outer, go to solo. Damaged pilot: trying to slow, full drag. Wingman: call rescue, head for channel. The pilot navigated a damaged aircraft to an emergency field, hands filthy and voice steady. The sensory record again is vivid. The smell of burning fuel, the sight of a wing stained with oil, the chatter of rescuers who smelled victory in surviving a ruin. A third tension moment is quieter but no less acute. It happened during a night return when engines faltered and navigation lights went out. The pilot, disoriented and alone, struggled to find a familiar landmark. The radio was jammed. He felt an isolation that foregrounded every instrument reading. His only options were to trust the compass, estimate wind drift, and conserve fuel. The tactile sensation of tiny course corrections through turbulent layers, the cold surface of the canopy, the slow, conscious breathing, and the near silence except for the engine tell a story of small decisions amplified. He landed at dawn on a runway never designed for fighters, and the crew worked with lamplight to bring him in. This scenario, described in the constrained sensory detail required, shows the constant low-level peril that pilots endured. As the plane matured in the field, so did the tactics. Squadron leaders codified boom and zoom metadata into briefings and simulated dogfights on the ground using maps and charts. Training emphasized energy state management and coordinated passes that used a lead element to draw attention while second elements concentrated fire. Pilots practiced convergence settings for their guns so that a burst at a given distance would create a strike pattern across a target. The effect of increasing ammunition capacity meant pilots could afford longer bursts when they found a stable firing solution, and that permitted a different kind of engagement calculus. Combat film later confirmed that concentrated short bursts at correct convergence distances produced catastrophic damage on the thin-skinned sides of enemy fighters and on the fuselage of bombers. Major operations demonstrated the strategic impact of the design en masse. During operations in support of D-Day and subsequent deeper strikes, the Thunderbolt and its variants performed multi-role tasks: close air support, bomber escort, and ground attack. The introduction of drop tanks extended range. Factories improved mounting points so added tanks could be jettisoned cleanly, and pilots could choose between range and loadouts. The engine upgrades added power. The propeller design optimized thrust, and the landing gear revisions improved survivability on makeshift fields. These upgrades were not abstract. They were battlefield multipliers. In one sortie sequence, films show Thunderbolts diving onto armored columns, unleashing cannons and rockets, then clawing back to altitude with smoke trailing and control surfaces punked by shrapnel but still functional. These operations demonstrated that the plane could be adapted quickly to new roles and that the logistical pipeline could keep up with variant production. Production numbers tell a blunt story. Factories that once made hundreds of smaller aircraft pivoted to a scale that produced thousands of Thunderbolts over months. The figure often cited tells of a production peak wherein many plants combined output to deliver a relentless flow of aircraft. Each line had to be fed by components from other factories and by supply chains that crossed oceans. Ammunition consumption rose proportionally. The demand for rounds required ordnance factories to ramp up metal forming and powder chemistry on a scale that strained transportation. Training facilities expanded and accelerated. New pilots were given abbreviated transition courses and sent forward. The strategic effect was to change the calculus of attrition. Where previously a superior maneuver doctrine could secure local victories, the ability to replace aircraft and to sustain sorties in depth meant that doctrine had to account for sheer throughput. There were costs. Casualty reports and repair logs show pilots lost in training and in combat and planes that never returned. Yet the plane's ability to return under fire and to be repaired mattered to overall effectiveness. Reports returned to command centers showing that aircraft often came back with dozens of hits yet still landed. Those metrics changed commanders' thinking about acceptable risk and permitted more aggressive escort profiles. At the same time, this forced the enemy to adapt. They adjusted tactics and increased emphasis on head-on attacks and on higher-caliber weapons to strip armor. Thomas Langley and other commanders met with analysts like Ingrid Bauer to adapt strategies informed by data, always weighing the tension between exposure and mission necessity. By the time large-scale operations across Europe reached their peak, the former scoff in an enemy cockpit had turned into a tactical respect captured in post-war interviews. Lieutenant Carl Weiss would later say, "We misjudged them. We thought fragile meant disposable. That was wrong." Such admissions were not the product of one battle, but of a pattern: survivability statistics, production rates, and the stubborn metrics of returned aircraft. The final toll of the campaign include numbers that are less poetic than they are decisive. Sortie rates per week, replacement rates, and percentages of aircraft returned with mission-critical systems intact. Those numbers tell the strategic story better than any single headline. The conclusion is both technical and human. The initial scorn was a reaction to appearance. The reality proved to be arithmetic plus endurance plus human adaptation. The decision to accept weight in exchange for armor and payload was a bet that the war would favor the side that could produce and sustain. It proved true in this theater: production backed doctrine, and doctrine adapted to machine. The P-47 Thunderbolt did not win by being the most graceful. It won by being able to take punishment, deliver overwhelming fire, and be manufactured in numbers that compensated for the chain of losses inevitable in sustained combat. 1 month after the major operation, the immediate effects were visible in squadron diaries. Pilots reported increased confidence in missions that prior to the change would have required more conservative profiles. Maintenance logs showed a drop in turnaround time as field teams learned the common failure modes and pre-positioned spare parts. Families in hometowns got letters from survivors who now wrote of tolerable risk rather than certain death. Statistically, mission success rates ticked upward and escort losses declined. The atmosphere among units shifted from anxious improvisation to a procedural competence that took its edge from the plane and from the system behind it. 3 months later, the strategic picture looked different. Enemy forces had begun to redeploy heavy fighters and to alter their training to account for the new threat of heavy-armed escorts. The battlefronts that once assumed air superiority now faced sustained resistance. Production lines were humming, and the logistical backbone had moved from makeshift adaptation to an industrial rhythm. Politically, the narrative around the plane grew into a story of industrial patriotism. Factories that produced thousands of airframes became points of civic pride. Retrospectives in periodicals highlighted the aggregated numerical advantage and argued that winning the war increasingly relied on the ability to keep machines in the air. 6 months on, the long-term effects took root. Pilots who had survived began to teach the next wave, codifying the new tactics into doctrine manuals. Air forces integrated heavy fighter concepts into training pipelines and mission planning. The enemy, pressed on multiple fronts, found it harder to rely on doctrine alone and had to diversify weapon systems. The plane's legacy extended beyond its own sorties. It reshaped expectations about what counted as advantage in air warfare and left a blueprint for how industrial capacity could be weaponized into tactical and strategic effect. In the last analysis, the story is simple and stubborn. The mockery of an enemy pilot that day over northern France was a miscalculation of what matters when war is fought in depth. Power, turbo-supercharger performance at altitude, ammunition capacity, and resilient structure combine to form a new kind of combat multiplier. The final testimony comes in a modest line from a captured German report, where an officer conceded that the machine had exceeded expectations. The line reads almost conversationally, but carries weight. "We did not expect this kind of endurance." That admission is both regret and recognition. If this episode teaches one lesson, it is that assumptions about elegance and superiority can blind strategists to the mathematics of mass and survival. Machines are not merely objects of beauty or speed. They are components of a system in which production, logistics, and human adaptation matter as much as maneuver. The P-47 Thunderbolt was not perfect. It was designed under pressure and improved through punishment. It was not the fastest nor the lightest, but it endured. In the end, that endurance changed the tempo of the skies and turned laughter into a memory. If you found this story striking, subscribe to follow more accounts that blend technical detail with human moments. We bring documents, pilot testimony, and factory records together so that the machines and the people who built them are both remembered. The thunder that once prompted a scoff became a signal that the side capable of manufacturing persistence had learned to shape the sound of victory.